Hello everyone, thank you for joining us today. My name is Alma Gallardo. Team Calypso is excited to present today our project Spacesuit Attachment Quick Release System, a challenge given by MicroG Next. This semester, Team Calypso continued working hard on revising the selected design from last semester. After receiving feedback from TSGC and considering NASA review, the team assessed and made the necessary modifications to the design to address concerns that arose from our last semester design. We're excited to share with you today the progress and results that we had this semester with our project. Thank you again for attending our presentation.
NASA is planning to return to the moon by 2024 with the Artemis program. On this mission, astronauts will be performing EVAs and they'll be carrying tools on the new XEMU spacesuit. There will be a utility belt attached to the spacesuit, and the belt will hold tools during the EVAs. In order for it to work properly, a quick release system is required to help astronauts work efficiently. NASA currently has a bayonet, probe, and receptacle system, but the system isn't suitable for the environment on the moon. NASA is seeking to update the system that they have, and that's where MicroG Next comes in. This program gives undergraduate students the opportunity to design and present a solution to real-life aerospace problems. Despite not being selected to continue through the program this semester, the team was willing and excited to continue with the design from iteration to manufacturing. In order to improve NASA's current receptacle system, we needed to identify any problems associated with the lunar surface and any other obstacles. The lunar dust on the moon's surface is very abrasive, magnetic, and adhesive. These properties altogether pose a challenge to the receptacle system's ability to tolerate dust on long mission cycles. In addition, due to the design of the current XEMU, astronauts' mobility and visibility is limited. NASA's current design is not dust tolerant. Dust can quickly fill up and clog the receptacle for the bayonet, thus preventing it from being inserted. Moreover, they have had complaints about the ergonomics for EVA use.
Listed are the design requirements from the Microg Next Design Challenge, with requirements 1 and 2 encompassing the most crucial engineering hurdles of the design challenge, 3 through 6 focusing on certain ergonomic features of the design, and 7 through 10 setting design parameters to ensure safety and portability. The ways in which Team Calypso succeeded in meeting and exceeding these requirements will be covered extensively during the testing portion of the presentation. Team Calypso used the requirements set by Microg and broke them into these design goals: dust tolerance, tactility, durability, safety, and simplicity. However, these design goals did not supersede the requirements from Microg Next. Rather, these summarized ideas help us work through the engineering design process as changes have been implemented from the start to today.
Over the past semester, Team Calypso, in accord with the engineering design process, has created a new version of the aisle design, focusing on addressing concerns and making improvements from the last semester. The new design, while having a redesigned profile, works under the same principles as the previous aisle system, in that the system is composed of an XEMU receptacle and a probe to be attached to an EVA tool. Moreover, the system utilizes the same method of having a ball-nosed spring plunger embedded within the bracket of the receptacle to apply pressure to the surface of the probe when inserted, thus preventing the probe from slipping out without the proper force being applied by the astronaut. The simplicity of this aisle design allows the system to be robust enough to handle the challenging lunar environment and removes unnecessary complexity which would become an added burden to the astronaut. The revised EVA tool probe attachment focuses on reducing unnecessary bulkage and improving the profile of the probe, allowing it to require less precision when entering the receptacle. A 4-leaf clover design was chosen to replace the previous square bracket, reducing the weight while retaining the same level of durability. In addition to this, the size of the probe has been reduced to 1/3 its original size, removing unnecessary weight from the probe while leaving sufficient material on the probe to enable it to hold the required 15-pound tool. Moreover, in response to NASA criticism indicating a potential failure mode, the size of the neck attaching the probe in the bracket has been further increased to prevent shearing from downward forces. Lastly, the profile of the probe has been changed from a U-shape into a V-shape, reducing the friction experienced by the probe when inserted into the receptacle, improving its ergonomics. Like its predecessor, this version of the IO receptacle supports an open design concept to allow dust from the lunar surface to pass through the system rather than accumulate within it. This is done using slots within the receptacle. The opening of the receptacle and the bracket were angled out to ensure that the opening has the maximum surface area for the probe to encounter for insertion from any direction, thereby improving the ergonomics of the interaction between the astronaut's tool and the receptacle. The modifications done to this IO system have significantly improved and developed the design from last semester, resulting in a product that better meets all the requirements set by NASA.
For testing of the IO design, we sought out to manufacture the device using NASA-specified materials. Unfortunately, our selected manufacturer failed to deliver on time for TSGC. Fortunately, the materials are primarily for preventing lunar sample contamination on the moon, and we were able to fully test the device and meet the requirements set by NASA using 3D printing. So, let's go see how the testing went.
Thanks for joining us for our presentation. After carefully taking into consideration the feedback that the team received from both NASA and TSGC, a new version of IO was designed, which not only works under the same principles as the original design, but also is more effective. The reiterations make the design less heavy and more durable. Many tests were conducted to ensure it successfully met NASA's requirements. Overall, the team is happy with the results that we had this semester and is excited to have had the opportunity to share it with everyone today.